Hello and welcome to my channel. We will be focused at IPv4 addressing and we will cover the fundamental aspects of IPv4 addressing in detail. It will include how to segment a network into subnets and how to create a variable length subnet mask as part of an overall IPv4 addressing scheme. We will see that subnetting is like cutting a pie into smaller and smaller pieces, and at the first it may seem overwhelming, but we will show you some tricks to help you along this way and to make that easier. The objective of this part is to calculate an IPv4 subnetting scheme to efficiently segment your network. And the topics that we will discuss will be the IPv4 address structure, where we will describe the structure of an IPv4 address, including the network portion, the host portion, and the subnet mask. We will see even the IPv4 unicast, broadcast, and multicast, where we will compare the characteristics and uses of the unicast, broadcast, and multicast IPv4 addresses. We will also see the types of IPv4 addresses, where we will explain the public, private, and reserved IPv4 addresses. We will check even the network segmentation, where we will explain how subnetting segments a network to enable better communication. We will see the subnet on IPv4 network, where we will calculate the IPv4 subnet for /4 prefix, and we will also see the subnet of /16 and /8 prefix, where we'll calculate the IPv4 subnet for each of those prefixes, and we will also see the subnet to meet requirements, where we will give a set of requirements for subnetting implement an IPv4 addressing scheme. And we will see even the variable length subnet masking, where we will explain how to create a flexible addressing scheme using variable length subnet mask. And finally, we will implement a variable length subnet mask addressing scheme at the structured design model. And for the moment, at this part of the IPv4 addressing, we will be focused at the three first topics. We have mentioned before that the IPv4 address is a 32-bit hierarchical address that is made up of a network portion and a host portion. When determining the network portion versus the host portion, you must look at the 32-bit stream as it is shown in this figure. And you have to see that the bits within the network portion of the address must be identical for all devices that reside in the same network. And the bits within the host portion of the address must be unique to identify a specific host within a network. If two hosts have the same bit pattern in the specific network portion of 32 bits, those two hosts will reside in the same network. The question is, how do the hosts know which portion of 32 bits identify the network and which identify the host? To solve this, we will need to know about the subnet mask. Assigning an IPv4 address to a host requires the IPv4 address, that is unique IPv4 address of the host, and a subnet mask that is used to identify the network host portion of the IPv4 address. Here in this figure, it is shown the IPv4 configuration of a Windows PC, and you can see there that it is configured even the default gateway that is required to reach the remote networks, and you can configure even the DNS server that are required to translate the domain names to the IPv4 addresses. The IPv4 subnet mask is used to differentiate the network portion from the host portion of an IPv4 address. When an IPv4 address is assigned to a device, the subnet mask is used to determine the network address of the device. The network address represents all the devices on the same network. Here it is shown the subnet mask with a 32-bit in decimal and binary format, as you can see. The subnet mask is a consecutive sequence of 1 bit followed by a consecutive sequence of 0 bits. To identify the network and host portion of an IPv4 address, the subnet mask is compared to the IPv4 address bit for bit from left to the right, as it is shown here. You can see that the subnet mask does not actually contain the network or host portion of an IPv4 address. It just tells the computer where to look for the IPv4 address that is the network portion and which part is the host portion. As you can see here, the 3 octet of the subnet mask that contain all bits in each octet once show the network portion, and where the subnet mask has 0, it shows the host portion. So if they compare the 3 octets of the IPv4 address with the subnet mask, it shows that the first 3 octets are the network portion and the last octet is the host portion. The actual process used to identify the network portion and host portion is called ANDing. Expressing the network address and host address with a dotted decimal subnet mask address can become cumbersome. Fortunately, there is an alternative method of identifying a subnet mask, and it is a method that is called the prefix length. The prefix length is a number of bits set to 1 in the subnet mask, and it is written in a slash notation, which is noted by a forward slash followed by the number of bits set to 1. Therefore, count the number of bits in the subnet mask and prepend it with a slash. If we refer to the table, we will see that the first column lists various subnet masks that can be used with the host address. The second column displays the converted 32-bit binary address, and the last column displays the following prefix length for each of them. And you can see that at the first line, the subnet mask is here, and it is shown here in the binary format, and as we say that we first write the slash, then we count the number of ones from left to the right, and then we write how much ones are there. So this is the prefix length for that subnet mask. And in this case, the subnet mask for the 255.0.0.0, it will be /8, and so it will go on. A network address is also referred to as a prefix or a network prefix. Therefore, the prefix length of the number of 1 bits in the subnet mask. When representing an IPv4 address using a prefix length, the IPv4 address is written followed by the prefix length with no spaces. For example, if we want to write the 192.168.10.10 with the subnet mask 255.255.255.0, it will be written as 192.168.10.10/24. Using various types of prefix length can be discussed in the other materials, and in the other slides. But for the now, we will be focused on /24. So we will be focused at this subnet mask. A logical AND is one of 3 Boolean operations used in Boolean or digital logic. There is the operation AND, OR, and NOT. The AND operation is used in determining the network address. Logical AND is the comparison of 2 bits that produce the results shown below. You will see that only 1 and 1 will produce 1, and any other combination will reproduce 0. In the digital logic, 1 represents true and 0 represents false. So when using the AND operation, both input value must be true so the result must be true. So both input must be 1, so the result should be 1. To identify the network address of an IPv4 host, the IPv4 address is logically ANDed bit by bit with the subnet mask. ANDing between the address and subnet mask yields the network address. To illustrate this, we have this example. We have the IPv4 address that is shown here in the decimal format, 192.168.10.10. Here it is shown in the binary format. We have the subnet mask 255.255.255.0. Here it is shown in the binary format, and by doing and bit by bit from left to the right, we will get the IPv4 network address that it is shown in the last line. And here in this example, we see that the network address will be 192.168.10.0. To explain the three types of addresses, we will be focused at this topology. And we have the network address, and it is an address that represents a specific network. A device belongs to this network if it meets three criteria. It has the same subnet mask as the network address, and as you can see here, they are all /24. It has the same network bits as the network address as indicated by the subnet mask, and as you can see, the first three octets for all the IP have the same number, so 192.168.10. It is located on the same broadcast domain as other hosts in the same network address. So this is the broadcast domain. Yes, they are in the same. A host determines its network address by performing an ANDing operation between its IPv4 address and its subnet mask. We have even the host addresses. Host addresses are addresses that can be assigned to a device such as a host computer, laptop, smartphone, web camera, printer, or router, etc., etc. The host portion of the address is the bits indicated by 0 bits in the subnet mask. Host addresses can have any combination of bits in the host portion except for all 0 bits or all 1 bits. When are all 0 bits is the network address, and where all 1 there is the broadcast address. All devices within the same network must have the same subnet mask and the same network bits. Only the host bits will differ and must be unique. We have the first host address and the last host address. The first host address within a network has all 0 bits in the last octet, except for the last bit that should be 1. So at the last octet, where there are 8 bits, the first 7 bits will be 0 and the last one will be 1. And at the last host, at the host portion, at that octet, the 7 first bits will be 1 and the last one, the 8 bit, will be 0. Any addresses between and including can be assigned to a device on network. We have even the broadcast addresses. There are addresses that are used when it is required to reach all devices on the IPv4 network. Let's see the table for the topology that we have. We have the subnet mask 255.255.255.0, or as it says /24. Here it is shown in the bit format, and there is the network portion, the first 3 octets where the subnet masks are all 1, and the host portion. So the network address will be the 192.168.10.0 because we said that the octet at the host portion, all bits must be 0. The first address is the address where at the host portion the first 7 bits will be 0 and the last bit will be 1. So 0 followed by 1 at the end. And it will be 192.168.10.1. The last address, we said that the host portion will be all ones followed by a 0. So 7 ones followed by 0. 192.168.10.254. And we have the broadcast address. And we say that the broadcast address at the host portion, all the bits will be 1. And it will be .255. A broadcast, remember this, that a broadcast address cannot be assigned to any device. In the previous slides, we learned that the structure of IPv4 address has a network portion and host portion. There are different ways to send a packet from a source device, and these different transmissions affect the destination IPv4 address. Unicast transmission refers to one device sending a message to another device on one-to-one communication. A unicast packet has a destination IP address that is a unicast address which goes to a single recipient. A source IP address can be only a unicast address because the packet can only originate from a single source. This is regardless of whether the destination IP address is, because it can be a unicast, broadcast, or multicast. This animation is the example of the unicast transmission. The broadcast transmission refers to a device sending a message to all the devices on a network in one-to-all communication. A broadcast packet has a destination IP address with all ones in the host portion. IPv4 address use broadcast packet, and IPv6 network does not have broadcast packets. A broadcast packet must be processed by all devices in the same broadcast domain. A broadcast domain identifies all hosts on the same network segment. A broadcast may be directed or limited. A directed broadcast is sent to all hosts on a specific network. For example, we have the host 172.16.4.1 that is at the network 172.16.4.0/24, and it sends a packet broadcast as 172.16.4.255. A limited broadcast is sent where all the bits at the 4 octets are all 1. By default, routers do not forward the broadcast. The animation shows a limited broadcast transmission. At the multicast transmission, we will reduce the traffic by allowing a host to send a single packet to a selected set of hosts that subscribe to a multicast group. A multicast packet is a packet with a destination IP address that is a multicast address. IPv4 has a reserved multicast range IP addresses that is from 244.0.0.0 to 239.255.255.255. Hosts that receive particular multicast packets are called multicast clients. The multicast client uses services requested by a client program to subscribe to the multicast group. Each multicast group is represented by a single IPv4 multicast destination address. When an IPv4 host subscribes to a multicast group, the host processes packets addressed to this multicast address and packets addressed to its uniquely allocated unicast address. Routing protocols such as Open Short Path First use multicast transmission. For example, routers enabled with Open Short Path First communicate with each other using the reserved Open Short Path First multicast address at 224.0.0.5. Only devices enabled with Open Short Path First will process these packets that have this IP as the destination IPv4 address. All other devices will ignore this packet. And here it is the animation that shows client accepting multicast packets. Just as there are different ways to transmit an IPv4 packet, there are also different types of IPv4 addresses. Some IPv4 addresses cannot be used to go out to the internet, and others are specifically allocated for routing to the internet. Some are used to verify a connection, and others are self-assigned. As a network administrator, you will eventually become very familiar with the type of IPv4 addresses, but for now, you should at least know that they are and when to use them. Public IPv4 addresses are addresses which are globally routed between Internet Service Provider routers. However, not all available IPv4 addresses can be used on the Internet. There are blocks of addresses called private address that are used by most organizations to assign IPv4 addresses to Internet hosts. At the mid-90s, with the introduction of the World Wide Web, the private IPv4 addresses are introduced because of the depletion of IPv4 address space. Private IPv4 addresses are not unique and can be used internally within any network. And these are the blocks of the private addresses and the prefixes for each of them. You should know that most internal networks, from large enterprise to home network, use private IPv4 addresses for addressing all internal devices, including hosts and routers. However, these private addresses are not globally routable. In this figure, we have three customers at the network 1, 2, and 3 and are sending packets outside their internal networks. These packets have a source IPv4 address that is a private address and a destination IPv4 address that is a public IP address. Packets with a private address must be filtered or translated to a public address before forwarding the packets to the IP. Internet Service Provider. Before the Internet Service Provider can forward these packets, it must translate the source IPv4 address, which is a private address, to a public IPv4 address using the network address translation. The network address translation is used to translate between private IPv4 and public IPv4 addresses. This is usually done on the router that connects the internal network to the Internet Service Provider network. Private IPv4 addresses in the organization's intranet will be translated to the public IPv4 addresses before routing to the Internet. Organizations that have resources available to the Internet, such as web server, will also have devices that have public IPv4 addresses. And as it is shown in this figure, this part of the network is known as the demilitarized zone. The router in the figure not only performs routing, it also performs network address translation and acts as a firewall for security. There are certain addresses, such as the network address and broadcast address, that cannot be assigned to a host. There are also special addresses that can be assigned to a host, but with restriction on how those hosts can interact within the network. We have the loopback addresses, and they are at the range of 127.0.0/8, and they are more commonly identified as only 127.0.0.1, and these are special addresses used by a host to direct traffic to itself. For example, it can be used on a host to test if the TCP/IP configuration is operating correctly. and it can be used by pinging at the, the loopback interface. We have even the link local address. They are at the range as it is shown here at the slide, and they are more commonly known as the automatic private IP addressing or as a PIPA address or self-assigned addresses. They are used by a Windows DHCP client to self-configure in the event that there are no DHCP server available on the network. Link local addresses can be used in a peer-to-peer communication but are not commonly used for this purpose. IPv4 addresses were assigned using classful addressing, and the customers were allocated a network address based on one of three classes. We have the class A with the range of the IP addresses as it is shown in the slide, and this class is designed to support extremely large networks with more than 60 million host addresses. Class A used a pixel/A prefix with the first octet to indicate the network address and the remaining 3 octets for host addresses. We have the class B with the range of the IP address as it is shown in the slide. It is designed to support the needs of moderate to large size network with up to approximately 65,000 host addresses. Class B used a fixed/16 prefix with the 2 high order octet to indicate the network address and the remaining 2 octets for the host addresses. And we have even the class C with the range of the IP address as it is shown on the slide, designed to support small networks with a maximum of 254 hosts. Class C can use a fixed/24 prefix with the first 3 octets to indicate the network and the remaining octet for the host address. As the time with a limited number of computers using the internet, classful addressing was an effective means to allocate addresses. And as it is shown here in this figure, class A and B networks had a very large number of host addresses, and class C has very few. Class A networks accounted for 50% of the IPv4 networks. This caused most of the available IPv4 addresses to go unused. That's why in the mid of 90s, with the introduction of the World Wide Web, classful addressing was depressed to more efficiently allocate the limited IPv4 addresses space. Classful address allocation was replaced with classless addressing, which is used today. Classless addressing ignores the rules of classes. Public IPv4 network addresses are allocated based on the number of addresses that can be justified. Public IPv4 addresses are addresses which are globally routed over the Internet. Public IPv4 addresses must be unique. Both IPv4 and IPv6 addresses are managed by the Internet Assigned Numbers Authority, where it manages and allocates blocks of IP addresses to the regional Internet registries. The 5 regional Internet registries are shown in this figure. And we have the Africa Network Information Center for Africa region. We have the Asia Pacific Network Information Center for Asia Pacific region. We have the American Register for Internet Number for North America region. We have the Regional Latin American and Caribbean IP Address Registry, which covers Latin America and some Caribbean islands. And we have even the RESUX IP European Network Coordination Center, which cover Europe, the Middle East, and Central of Asia. Thank you for being with me at this long video. Do not forget to subscribe at my channel for those who are new and hit the notification button for the new videos that will come up. And with those three topics, with IPv4 address structure, unicast, broadcast, and multicast addresses and the types of the IPv4 address, we are ending this first part of the IPv4 addressing, and see you soon with the other parts.